Welcome students. So till now we have seen what is a definite integral and how to evaluate it. There are two methods to evaluate a definite integral. One is by method of limit of sums and another is by method of antiderivatives. So we have seen that a definite integral a to b f x dx is equal to f b minus f a, where capital F x is antiderivative of small f x. There is a remark over here. We know that antiderivatives are not unique, and f x plus c dash will also give you the function f x. So we can evaluate the function, the integral, as f x plus c which is equal to. So what we see that this constant c is removed and we are getting the same value whether we are using capital F x as an antiderivative or f x plus c as an antiderivative of a small f x. So during definite integral the constant c can be ignored as it does not affect the value of the integral. Let us solve one more example to refresh our mind. Let us take integral so as you know that definite integrals can be interpreted as area. If this is your x axis, this is your y axis, then and this is line x equals to 0, this is line x equals to 1, then you can plot this function as so this will be half and this will be 1, 0 comma 1, 0 comma half. So this integral represents this area. This is the graph of 1 upon 1 plus x square. Now if I want to find out this integral by the method of antiderivatives, so I will be looking for a function whose derivative is 1 by 1 plus x square, and I hope all of you remember what is the antiderivative of 1 upon 1 plus x square. So you know that derivative of tan inverse x is 1 upon 1 plus x square. Therefore the value of this definite integral will be which is equal to, by the formula earlier explained, which is equal to tan inverse 1 is pi by 4 and tan inverse 0 is 0. So value of this integral is pi by 4. Given any definite integral of this kind, we can write the value of this integral in this form only if it is easy to find out antiderivative of small f x, i.e. that is it is easy to find out a function capital f x such that whose derivative is small f x, but it is a point to note here for all students that it is not easy to compute antiderivative of fx always, then what should we do? So, I will answer this question in next few problems. So, let us take one more example and see what will happen if we are not able to find out the antiderivative easily, and let us take this definite integral. Now, it is not easy to find out an antiderivative of this function integrand. So, we try to go for a trick, and the trick is, let us take that tan x is t. So, sec square x dx will be dt. So, this is now your dt. So, the integral will look like, this integral I will look like 2 tan x is t and sec square x dx is dt. Now, since you have changed the variable of the integration, so limits will change. So, when x is 0, tan 0 is 0, so t is also 0. So, lower limit x equals to 0 goes to t equals to 0. When x is pi by 4, tan pi by 4 is 1. So, new value of upper limit is 1. Now, you know the antiderivative of t, that will be t square by 2. So, value of the integral will be 1 minus 0 equals to 1. The trick that we have applied is known as method of substitution. In general, if you consider a problem of this kind, where the function is itself a function of another function, say gx, and you have g dash x into dx. If you have this kind of integral, then what you can do is, you can assume gx as your new variable u, then g dash x dx will be du. So, the integral I will be equal to f of u gx g dash x dx is du, and limits will change because you are integrating now with respect to u. So, when x is a, u is ga. So, x equals to a goes to, so the lower limit will be changed to ga, similarly the upper limit will be changed to gb. And it might be possible that for this integral you can very easily find out the antiderivative, that means capital Fx. So, this method is known as method of substitution. Let us solve some more complicated problems and see how to explore this method to solve even complicated problems. So, let us take this integral . Now, one remark over here that there can be several ways to solve this problem by choosing different substitutions, but one of them will be giving you the simplest solution. So, for example, if you take 1 by x to the power 3 by 2 as u, this may be one of the simplest possible solutions, substitutions possible for this integral. So, let us see what will be the limits. So, x equals to 1 will give you u equals to 1 by 2, x equals to 4 will give you u equals to 1 upon 1 plus 8, that is 1 by 9. So, this integral I will be one goes to 1 by 2 and 4 goes to 1 by 9. Now, differentiate this so that you find out the relationship between this integrand and du. So, for that let us differentiate this. So, you get minus 1 plus x to the power 3 by 2 square 3 by 2 x to the power half dx is equal to du. So, 3 root x dx by 1 plus x to the power 3 by 2 whole square d is equal to minus 2 du. So, this whole expression is now replaced by minus 2 du, minus 2 du, and you know what is the antiderivative of a constant. So, you get here u 1 by 2 to 1 by 9 minus 2 1 by 9 minus 1 by 2 minus 2 by 9 plus 1, that is 7 by 9. So, you can see that it seems initially very complicated to find out the antiderivative of the original integrand, but by this substitution it is very easy to solve the problem, and finally the transformed integral only constant is remaining whose antiderivative is known to you. Let us take another example. Now, so if we take x power 4 plus 9 as our new variable, say t, it might give you some approach to solve the problem, but it is better to assume this as t. You can try the previous substitution. I will be taking this substitution. So, if you take this substitution, see what happens. You get So, you get 2x cube dx by x to the power 4 plus 9 under root, this is equal to dt. So, this integral is converted into, so x cube dx by under root x power 4 plus 9 is dt by 2. So, you get dt by 2. what will happen to the limits? So if x goes to 0, t is under root 9, that is 3, and x goes to 2, t is 25 under root, that is 5, 3 to 5. So you get 1 by 2 is constant, you can take out, antiderivative is t, so you get 5 minus 3, that is 1. Let us take some more examples and solve it. That will help you in solving these kind of problems. So let us take following integral. You can see that if I assume this as our new variable, say u, so I get minus t to the power minus 2 dt goes to du. That means is minus du. When t goes to minus 1, u is 0, and when t is minus half, u is minus 1. So your value of the integral I is minus 1 goes to 0, minus half goes to minus 1, 4 times sine square u du. Now it is not easy to find out the antiderivative of sine square u directly, so we need to substitute it by a trigonometric identity, that is so we need to replace sine square u by this. So you get minus 2, 0 to minus 1, 1 minus cos 2u du, which is equal to minus 2 u minus sine 2u by 2, 0 to minus 1. So this will give you minus 1 minus 0 minus sine of minus 2 by 2 plus 0. So the value of the integral is finally 2 minus sine 2. So we have solved several problems, and we have seen that how the method of substitution can simplify several definite integrals. Apart from that, there are several other problems which may not be solvable by only method of substitutions. So there are several other properties of definite integrals which help in solving definite integrals. So we are going to learn those properties and prove it one by one. So properties of definite integrals. Property 1, this property says that changing the variable from x to t does not affect the integral at all. So, the proof of this property is one line, provided you assume that x is t. So, dx will be dt, and x equals to a will be replaced by t equals to a, and x equals to b will be replaced by t equals to b. And hence we have the property 1. Let us see property number 2. A to b fx dx is equal to minus of b to a fx dx. In particular, a to a fx dx is 0. We know that if small fx has an antiderivative, say capital Fx, then value of the integral is written as this. So, we can write it in this form. Hence, we can write it as this. Hence the property. Now for this, you can just replace b by a in this and see that the value is 0 by taking this to the other side, right hand side to the left hand side. Another explanation for this, that integration a to a is 0. Suppose fx is positive and the graph is like this, and so this integral will represent area under the curve. So if b will coincide with a, it is very easy to realize that the area will be 0. If this line b, vertical line b, is coinciding with vertical line a, the area will be 0. Hence this property. Therefore this property is true. Property 3. Property 3 says that you can break this integral in two definite integrals as summation, where c lies between b and a. So if capital Fx is antiderivative of fx, then value of a to b fx dx is equal to fb minus fa. Value of a to c fx dx is fc minus fa, and value of c to b fx dx is fb minus fc. So you start from this and you can just write here fb minus fc plus fc minus fa, and then you can use these two. So you get fb minus fa, you can replace by c to b fx dx, and this you can write replace by this using this equation. You get a to c fx dx. Hence the property 3 is true. Let us take property 4. Property 4 says that a to b fx dx is equal to a to b f a plus b minus x dx. So, this property can be very easily proved by just simple substitution. So, if you take x as a plus b minus t, so dx will be minus dt, x equals to a will go to t equals to b, x equals to b will go to t equals to a. So, this integral will become, this limit a will be converted into limit t equals to b, this b will go to t equals to a, x will be replaced by a plus b minus t, and dx is minus dt. Here you can use property 2 and you can interchange the limits because you have a negative sign. So, that negative sign, this negative sign will be cancelled out once you interchange the limits. So, you get a plus b minus t dt. Since property 1 says that variable t is dummy, so we can replace t by x, hence property 4 is established. All these properties are very important and we shall see it when we solve several examples by using these properties. Let us see property 5, which is a particular case of property 4, and it says that 0 to a fx dx is 0 to a f a minus x dx. So, you start with this left hand side again and substitute x by a minus t. So, you get dx as minus dt, x equals to 0 will give you t equals to a, substitute this, 0 will go to a, x equals to a will go to t equals to 0. So, you will get t equals to a and t equals to 0, fx will be f a minus t and dx is minus dt. By using property 2, you can interchange the limits. So, you get this negative sign will be, this negative sign will be cancelled. So, you get this. Now, if you replace t being the dummy variable by x, you get the RHS. This proves your property 5, very important property. We will see, we will solve a lot of problems by using this property. Property 6. Property 6 says something about this integral. So, we want to find out value of this integral, and so value of this integral you can write as 0 to a fx dx plus a to 2a fx dx by using property 3, because if this is 0, this is a and this is 2a. So, you can break this integral into two integrals by using property 3, where this is a, this is c, this is b. By using property 3, you can write like this. Now, let us see what can be the value of this integral. So, let us substitute x by 2a minus t. So, dx is equal to minus dt, x equals to a goes to t equals to a, x equals to 2a goes to t equals to 0. So, you get a goes to a 2a goes to 0, x is replaced by 2a minus t and dx is replaced by minus dt. By using property 2 we can interchange the limits again. So, this negative sign will be cancelled. So, we get 2a minus t dt, and by replacing this t again, because it is a dummy variable, we get f 2a minus x dx. So, 0 to 2a fx dx is equal to 0 to a fx dx plus a to 2a fx dx, and value of this is computed as this. So, we can replace it here. So, we get final formula, that is 0 to a f 2a minus x dx. This is your property 6. Let us deduce another property from this formula, that is property 7. So, as we have seen that 0 to 2a fx dx is equal to 0 to a fx dx plus 0 to a f 2a minus x dx. Now, if f 2a minus x is equal to fx, then equation say 1 will give you, that is property 6 will be simplified into this, and if f of 2a minus x is equal to minus of fx, in that case this property 6 will be simplified and you will be getting 0. So, this is property 7. It says that this is equal to this if this condition is true, and if this condition is true, then this property. We will see that how these properties are going to help us in solving some complicated problems. Now, let us prove last property, that is property 8. Property 8 says that minus a to a fx dx is equal to, there are two possibilities. If fx is even function, then this is equal to 0 to a fx dx, and if fx is even, and value of this integral is zero if fx is odd. So, an even function satisfies the following property, that is f of minus x is fx, and odd function satisfies that f of minus x is minus of fx. So, let us prove this property. So, by using property 3 we can write this integral as this. Now take this integral and simplify it by using the properties of even and odd functions. So replace x by minus t, we get dx as minus dt, and minus a will be replaced, x equals to minus a will be replaced by t equals to a, and x equals to 0 will be replaced by t equals to 0. So we get a 0 f of minus t minus dt. So this is equal to, by using property 2 we can interchange the limits and this minus sign will get cancelled, and we get this. Since t is dummy variable, so we can replace t by x. So finally we arrived at dx equals to minus, sorry, we got this as 0 to a f of minus t dt plus 0 to a f of t dt. So minus a to a fx dx we got as 0 to a f of minus x dx. Since the variable is dummy, so we can replace it by x, 0 to a f of x dx. Now if fx is even, that is i.e. f of minus x is fx, so minus a to a fx dx will be twice of 0 to a fx dx, and if f of minus x is minus of this, we get this value as 0. So let us solve some simple problems and see how these properties of definite integrals can be utilized in solving definite integrals very easily. Example 1. Let us solve 0 to 4 mod x minus 2 dx. Now if I ask you what is the antiderivative of mod of x minus 2, can you answer this? It is not easy to find out the antiderivative of this. So what we do, we use property 3 and break it in two parts, because mod of x minus 2 is equal to minus of x minus 2 when x is less than equal to 2, and x minus 2 when x is greater than or equal to 2. So we can break it in two parts and write in simple polynomial form. So we can write it like this, and integrate it simply. So here we are using property 3. So this will give you zero to 2, 2 to 4, So, by applying the formula of definite integrals by method of antiderivative, we get so final answer is 4. So, you can see that how property 3 can be utilized in finding out a little complicated problem. Let us take another example. So, we are going to use a property which says that 0 to a fx dx is same as 0 to a f a minus x dx. So, therefore, I will be equal to 0 to pi by 2 4 times by this property, this I and this I will be same, this integral, value of this integral and value of this integral will be same. So, I get this equal to, so pi by 2 minus x is in the first quadrant. So, therefore, we get cos x under root cos x plus under root sin x dx. Now, if we add say 1 and say this is 2, so by adding 1 and 2 we will get 2I on the left hand side, and on the right hand side once both the right hand side will be added, we will be getting only 4 dx, that is 4 into value of this integral will be pi by 2, 4 into pi by 2. So, therefore, I is equal to pi, final answer. Let us take another example. Twice of 0 to pi by 2 log cos x dx. We can write this integral as by using the property which will give us I as now. So, we add 1 and 2 and we get that I 2I is equal to 2 times 0 to pi by 2 log of sin x plus log of cos x dx. So, this I is equal to 0 to pi by 2 log of sin x cos x dx. So, if you multiply and divide by 2 here, so you get I as 0 to pi by 2 log sin 2x dx minus 0 to pi by 2 log 2 dx. So, I is equal to, if you take 2x equals to t in this integral, 0 will go to 0, x equals to 0, t is 0, x pi by 2 t is pi, and log sin t dx will be 1 by 2 dt minus pi by 2 log 2. So, we got 1 by 2 0 to pi log sin t dt minus pi by 2 log 2. Now, in this integral we can write here this as pi by 2 into 2 and apply the formula 0 to 2a fx dx is equal to twice of 0 to a fx dx, provided f2a minus x is fx. If you apply that, we get I equals to 1 by 2 into 2 0 to pi by 2 log of sin pi minus t dt minus pi by 2 log 2. So, therefore, I is equal to 0 to pi by 2 log sin t dt log 2, and we know that from our previous calculation what is the value of this. Let me show you. So, by previous calculation value of this, by previous calculation value of this is I by 2. So, we got finally I equals to I by 2 minus pi by 2 log 2. Therefore, I by 2 is minus pi by 2 log 2. So, therefore, I equals to minus pi log 2. So, this was a very complicated problem, and you see how this properties of definite integrals helps you to solve this problem. Let us take another problem. 0 to 1 so again using the property that this is equal to 0 to a f a minus x dx, we can write I equals to 0 to 1, x will be replaced by 1 minus x, 1 minus 1 minus x to the power n dx. We get 0 to 1, 1 minus x, x to the power n dx, which is equal to 0 to 1 dx. Hence, by integration you get zero to 1, which gives you, so which is equal to let us take one more problem. I equals to 0 to pi x dx upon 1 plus sin x. So, this will be equal to 0 to pi minus x 1 plus sin pi minus x dx. So, therefore, I is equal to 0 to pi minus x dx by 1 plus sin x. So, if we add this integral with this integral, we get 2I equals to 0 to pi dx upon 1 plus sin x. So, 2I is equal to 0 to pi is constant, so we can take out, and this can be written as sin x by 2 plus cos x by 2 whole square. This can be written as 0 to pi sec square x by 2 dx upon 1 plus tan x by 2 square. Now, let tan x by 2 is t. So, sec square x by 2 dx equals to dt half. So, you get 2I equals to pi, tan 0 goes to 0, tan pi by 2 goes to infinity, and sec square x by 2 dx is 2 dt, and here you get 1 plus t square. So, this will give you minus 2 upon 1 plus t, integration of this 0 to infinity. So, this gives you pi is there. So, pi minus 2 pi 0 minus 1. So, final value of I you get as 2I is equal to 2 pi. So, I is equal to pi. Here again we have used this property 0 to a fx dx equals to 0 to a f a minus x dx, and then we have used substitution also, and then there are some trigonometric identities are also there. With this I stop, and later we will consider some more complicated problems and explore more about definite integrals and about their applications in finding out area of complicated shapes bounded between 1 curve, 2 curve, 3 curve, 4 curves and so on. Thank you.